The concept of static equilibrium is central to the study of engineering mechanics and structures. A structural system, be it a building, a tower, a bridge, or any other load-carrying mechanism, must remain at rest when subjected to loads. For example, a building would be of little use if it undergoes rigid body motion, say, due to the wind load. When a structure can withstand loads without this type of movement, we say it is in static equilibrium. In this lecture, we are going to talk about the mathematical definition of static equilibrium and its role for engineering analysis. But instead of using systems like buildings and bridges in our discussion, we are going to use a much simpler system, a particle. A particle could be an object whose dimensions are negligible, or could be a point in a larger, more complex system. We will talk about static equilibrium pertaining to more complex rigid bodies in future lectures. Consider this particle. For it to remain at rest, for the particle to maintain its static equilibrium, the net force acting on it must be zero. A non-zero net force would cause the particle to move. Therefore, given a particle subjected to two or more forces, we can write the condition of static equilibrium this way. This equation states that for the particle to be in equilibrium, the net force vector acting on it must be zero. In two-dimensional space, where vectors are described in terms of their x and y components, we can write this vector equation in terms of two equations, like this. We call these static equilibrium equations. We can use these equations in two ways. If all the applied forces are known, the equations could tell us if the particle is in equilibrium. Alternatively, if some of the forces acting on the particle are unknown, we can use the equations to calculate them. For example, this particle is subjected to two forces. Does the particle remain at rest? Is it in the state of equilibrium? To answer the question, we need to see if the two forces add up to zero, if the equilibrium equations are satisfied. Here, we need to write only one of the two equilibrium equations, since all the forces act in the horizontal direction. Here is the equation. Obviously, the forces add up to zero, so the particle is in equilibrium. Now consider this particle. It is subjected to three forces. We know the magnitude and direction of two of them, but the magnitude of this force is unknown. We wish to determine r, such that the particle remains in equilibrium. Since two of the forces have both x and y components, we need to write both equilibrium equations. The net force in x direction must be zero, and the net force in y direction must be zero. Since r appears in the first equation only, if we solve it for the unknown, we get. We also need to check the second equation to make sure it is satisfied. Yes, the sum of the forces in y direction is indeed zero. What does this negative sign mean? It means the direction of the vector is opposite to the direction shown on the diagram. Put it differently, for the particle to be in equilibrium, the horizontal force must be pointing toward the particle. We can show the result of our simple analysis either this way, by writing negative 13.86 next to the vector pointing away from the particle, or we can write positive 13.86 for the force magnitude, but reverse the direction of the arrow like this. These two representations mean the same thing. Since this is an important point, let me restate it. We either leave the direction of the force unchanged and specify its magnitude with a negative sign, or we change the direction of the arrow and change the force magnitude from negative to positive. But we do not do this. That would be an incorrect representation of the result. Let's go over a simple example. Suppose we are given this system consisting of 2 flower pots and the ropes that secure them vertically. If no other external forces are applied to the system, we can say that the system is in static equilibrium. That is, no rigid body movement takes place here. Assuming that each pot weighs 45 newtons, we wish to determine the tension force in the ropes. For the purpose of determining these unknown forces, we can view this as a particle equilibrium problem. Where is the particle? There are many particles in this system, but we are not interested in most of them. We are only interested in the ones that enable us to determine the unknown forces. So, we are looking for a particle that sits at the intersection of the relevant forces in our system. If we replace each pot with a downward force of 45 newtons, we should be able to see where the particles of interest are located. At the tail end of the applied force vectors where the ropes and the pots come together. So, points A and C act as our particles of interest. Note that here we have 2 independent particles, as they have no forces in common. Hence, we need to solve 2 independent particle equilibrium problems. Here's particle A and the forces that are acting on it. We have a downward force of 45 newtons and an upward force with an unknown magnitude. This force represents the tension in rope AB. For the particle to be in equilibrium, the net force in y direction must be 0. So we can write solving this equation for the unknown force, we get FAB equals 45 newtons. That is, tension in segment AB is 45 newtons. This is rather obvious, since if the pot weighs 45 newtons, then we need a force of 45 newtons in the rope to hold the pot in place. Particle C is subjected to 3 forces. A downward force of 45 newtons, the force in segment CD, and the force in segment CE. Given these distances, we can determine the angle between each rope segment and the vertical axis. Since the 2 angles are equal, let's use the same label for both. Tangent of beta equals 25 over 50, so angle beta equals 26.57 degrees. Here, we need to write 2 equilibrium equations, since we have forces with x and y components. The net force in x direction must be 0, and the net force in y direction must be 0. Assuming x is positive to the right and y is positive upward, we can write solving these equations for the unknown force magnitudes, we get. This means, for the pot to remain in place, each rope segment must carry a tension force of 25.16 newtons. In summary, in 2-dimensional space, particle equilibrium involves writing 2 equations. Therefore, we can analyze problems with up to 2 unknowns given a single particle. We can use the concept of particle equilibrium to solve a host of practical problems. See if you can solve the following problems.